The first thing we are going to learn about is determining whether an ordered triple pair satisfies the following system. Step 1 is to plug the solution into each equation and see if it is true. So for the first one, you plug everything in and it's true. It's also true for the second one and the third one. So the ordered triple does satisfy the system. Next, we are going to learn how to solve a system of equations by using elimination. So we have our first equation being 5x minus 2y minus 4z equals 3. Second equation is 3x plus 3y plus 2z equals negative 3. And our third equation is negative 2x plus 5y plus 3z equals 3. Step 1 is to reduce the system to two equations and two variables. To do that, we're going to use elimination. We're going to use the first two equations. Then we are going to get rid of one variable, in this case z. So we leave the first equation alone and we multiply the second equation by 2 to get 5x minus 2y minus 4z equals 3 and 6x plus 6y plus 4z equals 6. Then we're going to add the two equations together to get 11x plus 4y equals negative 3. That is going to be equation number 4. We're going to do the same thing for two other equations, in this case number 2 and 3. And we multiply the top one by negative 3 and the bottom one by 2 to get negative 9x minus 9y minus 6z equals 9. Negative 4x plus 10y plus 6z equals 6. We're going to add those two together to get negative 13x plus y equals negative 15. That is going to be our fifth equation. Then step 2 is to solve the resulting system of two equations in two variables. To do this, we take equations 4 and 5 and get rid of another variable, in this case y. So the first equation we leave alone, and the second equation we multiply by negative 4 to get 11x plus 4y equals 3 and 52x minus 4y equals negative 60. Then we add those two together to get 63x equals negative 63 and x equals negative 1. And so our third step is to use back substitution in one of the equations in two variables to find the value of the second variable. To do this, we take one of the original equations, negative 13x plus y equals 15. Then we substitute what we found for x in, and we get y equals 2. Then step 4 is to use back substitution using the two found variables into one of the original equations to find the value of the third variable. So we're using equation number 2. You plug in what x and y equals and solve, and z equals 3. So our solution is negative 1 to negative 3. Next, we are going to solve a system of equations with one of the equations missing a term. Step 1 is to reduce the system to two equations in two variables. To do this, we take equations 2 and 3 and get rid of the already missing variable, in this case y. we multiply the top equation by -2 and leave the bottom equation alone to get -2x minus 2y minus 4z equals -34, and x plus 2y plus z equals 16. We add those two together to get equation number 4, which is -x minus 3z equals -18. Step 2 is to solve the resulting system of two equations in two variables. To do this, we take our first and fourth equation and get rid of one of the variables, in this case x, and we don't have to change either of the equations. So we get -2z equals -10 and z equals -5. So step 3 is to use back substitution in one of the equations in two variables to find the value of the second variable, which would be, we're using equation number 1, which is x plus z equals 8. We substitute 5 in and we find that x equals 3. Then step number 4 is to use back substitute the values found for two variables back into one of the original equations to find the value of the third variable. So in this case we're using equation number 2. We substitute in x and z and solve for y. In this case y equals 4. The solution is 3, 4, and 5. Next, we're going to have a model of data relating sleep and death rates, and we're going to use that model to create a function. To do this, we start by plugging each x and y pair into the function y equals ax squared plus bx plus c. So we take the x and plug it into each x value and the y into each y value, and we get our three equations. Step 2 is to eliminate and reduce the system to two equations in two variables. For this, we're going to eliminate c. We're using the first and second equations. The first equation we're not going to change, and the second equation we're going to multiply by -1, so that we get 16,082 equals 16a plus 4b plus c, and -626 equals -49a minus 7b equals c. And so our fourth equation is 1056 equals -33a minus 3b. We're going to do this for our other two equations, 2 and 3. The first one we're going to leave the same. The second one we're going to multiply by -1, and we get -49a plus 7b plus c equals 626, and -81a minus 9b minus c equals -967. And our fifth equation is -32a minus 2b equals -341. And step 3 is to solve the resulting system of two equations into two variables. To do this, we take equations 4 and 5, and we're going to get rid of variable b. We multiply the first one by -2 and the second one by 3 to get -2112 equals 66a plus 6b, and -1023 equals -96a minus 6b. And then we add those two together to get -3135 equals -30a, and a equals 104.5. Step 4 is to use back substitution in one of the equations in two variables to find the value of the second variable. So we're going to use equation number 4, and we're going to substitute in A. So we get B equals negative 1,501.5. Then step 5 is to back substitute the values found for two variables back into one of the original equations to find the value of the third variable. So we're going to use equation number 1 and substitute in A and B to find C, which is 6,016. Then step 6 is to plug the variables back into the equation. Y equals ax squared plus bx plus c, and you get y equals 104.5 x squared minus 1,500.1.5 plus 6,016, or f of x equals 104.5 x squared minus 1,501.5 x plus 6,016.